There we go. So we're going to start off by finishing up. So this is question number, make sure I have the right number. It's question 3.15. So again, in the last lecture, we did the first two parts of question 3.15. And right now we're going to finish the last part of question 3.15. And just to refresh your memory, we have this balanced equation that 2 molecules of ammonia react with 1 molecule of carbon dioxide, produce 1 mole of urea, and we get a mole of water. So there's our balanced equation. We also looked up the molar masses for ammonia and for carbon dioxide. And so for ammonia, the molar mass is 17.03 grams per mole. For carbon dioxide, it's 44.01 grams per mole. And that's all we need to know right now. Now, again, we already figured out that ammonia was the limiting reactant, right? We did that in our last question, okay, the last lecture, sorry. And what else? We know that we were reacting 637.2 grams of ammonia with 1,142 grams of carbon dioxide. So what's happening here is we know that we are going to consume all of the ammonia, but we're going to have some carbon dioxide left over, right? We're not going to use up all of this 1,142 grams in its entirety. We're going to use some of it, but not all of it. So what we need to do is to figure out how much of that carbon dioxide is getting used up. And I think the best way to solve that is to use dimensional analysis, because we know we're consuming all of this ammonia, right? So if we can relate the number of moles of ammonia that we have here to the number of moles of carbon dioxide, we can figure out exactly how much carbon dioxide was consumed in the reaction. So we can set up a conversion factor here that will give us the number of moles of ammonia by using the molar mass of ammonia. So we have 17.03 grams of ammonia in 1 mole of ammonia. And then in order to get the number of moles of carbon dioxide, I have to use the balanced equation. And I know that for every 2 moles of ammonia that I consume 1 mole of carbon dioxide. So let's plug that in. 2 moles of ammonia, and I end up consuming 1 mole of CO2. When I punch all of this into my calculator, okay, that's going to tell me the number of moles of carbon dioxide that was used up. All right, so let's do that. And so you can see that grams of ammonia, moles of ammonia are going to cancel out, and we're going to be left over with the number of moles of CO2. So we end up using up 18.71 moles of CO2, like that. So that's the number of moles of CO2 that we used up. Now, there's a few ways that you could do this. You could either leave it like this and figure out, like we've just done, figure out the number of moles, or you could figure out the number of grams. And so I'm going to backtrack. So I'm going to delete this, and I'm going to go one more step. I'm going to say, well, I know that in 1 mole of CO2, I have 44.01 grams of CO2, like that. And so the moles of CO2 are going to cancel out like this. And now we're going to get the mass of carbon dioxide that we consume, the total mass that we consume. So let me get my calculator here. We got 637.2 divided by 17.03, divide that by 2, and then multiply by 44.01. And that gives us 823.3 grams of CO2 that was used. But remember, we had this much CO2 available, okay, available. And so the question is, how much excess reagent in grams is left over? So we could put here CO2 left over. The amount of CO2 left over is going to be equal to 1,142 grams of CO2, subtract 823.3 grams of CO2. And when you punch that spinach into your calculator, you end up with 319 grams of carbon dioxide that is going to be left over. And so that is the answer and the solution to C. All right, so we get that one down. Let's move on and try another one. Let's try this one here. Example 3.16. So let me go back to my slides over here. I have to find it. So 3.16 is right here. Okay, and I left myself some room. So it says here, the reaction between alcohols and halogen compounds to form ethers is an important reaction in organic chemistry, as illustrated here for the reaction between methanol. So this molecule here, this is methanol, and methyl bromide, shown here, to form dimethyl ether. So this is dimethyl ether right here, which is a useful precursor to other organic compounds or as an aerosol propellant. This reaction is carried out in a dry or water-free organic solvent. And the butylithium, so this is butylithium right here, serves to remove a hydrogen ion from methanol. Butylithium will also react with any residual water in the solvent, so the reaction is typically carried out with 2.5 molar equivalents of that reagent. So what that means is that if you have, all they're saying here is that if you have 1 mole of methanol, you would have 2.5 moles of butylithium. Now you're like, well, that's not a balanced equation. No, it's just saying that you set the reaction up that way. You typically carry it out by adding too much, right? You add more than enough. So the question is, how many grams of methyl bromide and butylithium will be needed to carry out the preceding reaction if we start with 10 grams of methanol? All right, well, we have a balanced equation, but remember, for every 1 mole of methanol, we're going to use up 2.5 moles of butylithium. And for every 1 mole of methanol, we're going to use up 1 mole of methyl bromide. All right, so something that I haven't done already is I see that I solved this problem, but I didn't look up the molar masses. So maybe I'll get some of my students to help me out with this. So I'm going to move over here and rewrite the equation. So let's start by doing that. We have methanol. So methanol plus methyl bromide plus butylithium produces dimethyl ether. This compound, lithium bromide, and also this other compound here, this is butane, like in a butane lighter. Okay, now it's telling us that we're starting out with 10 grams of methanol. So we're starting out with 10.0 grams of this, and we want to know the mass of methyl bromide, and we want to know the mass of butylithium that's used up. So we want to know the mass here too. All right. And again, they told us that when you use 1 mole of methanol, you're going to also use 1 mole of this, but you're going to use 2.5 moles of butylithium, like that. So again, I haven't looked at the molar masses, so I'm going to do that right now. I'll just get them quickly here. So methanol's molar mass is 32.04 grams per mole. Methyl bromide's molar mass is 94.94 grams per mole. And butylithium's molar mass is 64.1. So we'll put here 60.1 grams per mole. All right, so let's start out by figuring out the mass of methyl bromide that we're going to use up. Okay, so let's start. We're starting out with 10.0 grams of methanol, CH3OH. We know the molar mass of methanol right here, and we can use that conversion factor. For every 1 mole of methanol, I have 32.04 grams of methanol, like that. Again, we've done this many, many times in this class, but just to reiterate, if it helps you out, if we were to stop right here, what would we have? We'd have the moles of methanol. But in order to get the mass of methyl bromide, we're going to need the number of moles of methyl bromide. How am I going to get that? Where am I going to go to get that? Who could tell me? Where would I get my next conversion factor? Not a trick question. Can you see in the chat here? Anyone? Where would I go to get a conversion factor? Yeah, exactly. Tyler says from the balanced equation. Couldn't agree more, right? And I know that when I use up one, I'll go back to blue here. When I use up 1 mole of methanol, I also use up 1 mole of methyl bromide. Methyl bromide. And I want to figure out the mass of methyl bromide, so I'm going to use the molar mass of methyl bromide, which is 94.94 grams of methyl bromide in 1 mole of methyl bromide, like that. And looky, everything's going to work out. My grams of methanol cancel, my moles of methanol cancel, my moles of methyl bromide cancel, and I'm left over with grams of methyl bromide. Now, I've already done the math, but I'm going to double check. Divided by 32.04 times 94.94. And you end up with 29.6 grams. So 29.6 grams of methyl bromide is consumed. So we've got that one done. All right. I got 50 grams of butyllithium, but I'm going to double check myself. So I'm starting it with my 10.0 grams of methanol. And I know my molar mass of methanol, which is 1 mole of methanol, contains 34.04 grams of methanol. I go to my balanced equation. I know that when I use 1 mole of methanol, the problem told me that I want to use 2.5 moles of my butyllithium. So we'll put that in. And then again, if I was to stop here, grams of methanol cancel. Moles of methanol cancel, and I would have moles of butyllithium, but I want the mass of butyllithium, and so I'm going to use the molar mass of butyllithium, which is 64.1 grams of butyllithium in 1 mole of butyllithium, like that. Okay, let's double check the units. Yes, moles of butyllithium cancel out. I got 50. Again, I'm going to double check it here, divided by 32.04. Times 2.5 times 64.1. Yeah, 50.0. So it gives you 50.0 grams of butyllithium. Okay, so I would say that this question is even maybe an order of magnitude simpler than question 3.15 because it's not a limiting reactant problem. It's just a problem where we get to practice our stoichiometry, right? Have a balanced equation, figure out number of moles, compare number of moles of different reagents and products, right? So you have to be very strong in this because, as you can see, it's a big part of, it's a big part of chapter 3. And this same kind of math is going to continue on in chapter 4 as well. Well, we've come to the end of chapter 3. We have one concept left, and that is the concept of reaction yield. So the theoretical yield, so if you've ever heard of a theoretical yield before, maybe yeah, maybe no. It's the amount of product that would result if all of the limiting reagent reacted. What that's saying is, theoretically, have you ever heard somebody say in your everyday life, well, in theory, I would do this, and theoretically, this should happen. Theoretically, that should happen. What that means is theoretical yield is really best case scenario. So best case scenario. Okay, that means if everything reacts. So every reaction that we've looked at now, it says, oh, figure out how many grams of this product will be formed. Every time we did that, we were using we were assuming a theoretical yield of 100%, that everything was going to react. Now, an actual yield, this is more like in reality, okay? In reality, okay? This is more like what happens in the real world. Now, that's me being a little bit tongue-in-cheek, but what actual yield means is the actual amount of product that you're going to obtain from a reaction. So this has happened to me, hundreds of times in my life where I'd set up a reaction when I worked in industry, and I'd say, okay, I'm going to end up with, if I calculate the theoretical yield, I should end up with 1 gram of this compound. I want to get I want to get 900 milligrams, so that's 90%. So yeah, this should work. Then I'd set it up, and I'd end up with 500 milligrams. So I'd only end up with half, or a 50% yield. Okay, and sometimes that can be really disappointing, but that is why we always want to now analyze our reactions and determine their percent yield. So the percent yield is what you get, the actual yield divided by what you should get, and multiplied by 100%. The first job I ever had in industry, I was, very frustrated by a reaction one time, and the person that I shared my office with had a lot more experience than me, and I'll never forget what he said. He said, "Well, you know what, Dan?" He said, "Molecules are going to do what they're supposed to do, and atoms are going to do what they're supposed to do. So, we just have to find a way to get them to do what we want them to do." Anyhow, let's take a look at this question here. It says titanium is a strong, lightweight, corrosion-resistant metal that is used in rockets, aircraft, jet engines, bicycle frames. If you're into camping, sometimes you can buy like titanium cookware for camping because it's really light if you want to go hiking. Anyhow, it is prepared by the reaction of titanium 4-chloride with molten magnesium between 950 and 1,150 degrees Celsius. It says that in a certain industrial operation, you take 3.54 times 10 to the 7 grams of titanium chloride, and you react it with 1.13 times 10 to the 7 grams of magnesium, and you're like, that's a lot. Well, okay, remember, it's an industrial application. And it says, calculate the theoretical yield of 10 in grams. So if you wanted to get some practice in limiting reactants, well, here's another problem that deals with limiting reactants, because in order for us to determine the theoretical yield, we've been given a balanced equation, but in order for us to determine the theoretical yield of titanium, we're going to have to run the math both on this mass of titanium chloride and this mass of magnesium, okay, and determine which one gives us the least amount of product, and that's going to be the limiting reactant, and from that we can determine the theoretical yield. After we've determined the theoretical yield, it just asks us what would be the percent yield if you actually ended up with this much titanium. So we know that what we get for a theoretical yield must be less than this, right? Theoretical yield must be less than. Okay, it's got to be less than that number. All right, let's see if we can figure it out. Would you guys like me to give you 2 or 3 minutes to tackle the problem, to give it a try first, or would you like me to just kind of go through it? Who would like a few minutes to give it the old college try? Anyone? What does Shay say? Go through. Okay, well, let's go through it then. Okay. Now, I've already gone ahead and I've done some of the math in this one already. Not all of it, but I've done some of it. We know that we're starting out with 3.54 times 10 to the 7 grams of titanium chloride. We know from the problem that we're starting out with 1.13 times 10 to the 7 grams of magnesium, right? And we're trying to figure out the theoretical yield. So we want to know the yield, theoretical yield. I'll put here theo yield of titanium in grams. Okay, so some more information that I'll put up here that you're going to need is that the molar mass of titanium 4-chloride, TiCl4, is 189.7 grams per mole. The molar mass of magnesium is 24.30 grams per mole. Of course, I just got that from the periodic table. And the molar mass of titanium is 47.90 grams per mole. All right, I'm going to move that out of the way. Oops, didn't mean to do that. There we go. Why don't I just move it up here? All right, so we have everything that we need. Well, let's get started here. All right, so where are we going to start? Let's start with our titanium 4-chloride. And we have 3.54 times 10 to the 7 grams of titanium 4-chloride. Now, again, we want to figure out the mass of titanium that's formed, so we need to figure out the number of moles of titanium 4-chloride first. And we know that we have 189.7 grams of titanium 4-chloride in 1 mole of titanium 4-chloride. Look, if I was to stop right here, okay, all I would end up with would be moles of titanium chloride. I don't want that. I want moles of titanium, so I need to go to my balanced equation. Since there are no numbers, there are no coefficients in front of titanium 4-chloride, nor in front of titanium, that means that we have 1 mole of each of these. So I know that for every 1 mole of TiCl4, titanium 4 chloride, that's consumed, I form 1 mole of titanium. Okay, good. Look, moles of titanium 4 chloride cancel. Now I want to get the mass of titanium, and so I need 1 more conversion factor, and I know that in 1 mole of titanium, I have 47.90 grams. So 47.90 grams of titanium. Now, let's make sure our units cancel. Yes, let's do some math. So we have 3.54 times 10 to the 7 divided by 189.7 times 47.9. And we end up with 8.9. I get 8.94 times 10 to the 6th grams of titanium. Okay, so again, this is what we would get if we had this much titanium 4 chloride and all of the magnesium at our disposal, but we know that's not true. We only have this much magnesium, and so we need to run all of these calculations again, but now we're going to start out with our magnesium, and we know that we have 1.13 times 10 to the 7 grams of magnesium, and I know that in 1 mole of magnesium, I have 24.30 grams, 24.30 grams of magnesium. From my balanced equation, I know that for every 2 moles of magnesium, I form 1 mole of titanium. So 2 moles of Mg gives me 1 mole of titanium. And my last conversion factor is going to be the same one that I used here, right? It's going to be that for every one mole of titanium, I'm going to end up producing 47.90 grams of titanium. Looky, looky, all of my units cancel. Grams of magnesium, moles of magnesium, moles of titanium. All right, so let me try putting that in the old calculator here. So I have 1.13 times 10 to the 7 divided by 24.30 divided by 2 multiplied by 47.9. And when I do that, I get a big number, which is equal to 1.11 times 10 to the 7 grams of titanium. Well, which one of these numbers is less? 8.94 times 10 to the 6 or 1.11 times 10 to the 7? Well, obviously, it's the 8.94 times 10 to the 6. And so that tells us that what? It tells us that TiCl, the titanium 4 chloride, is the limiting reactant, and the theoretical yield of titanium is 8.94 times 10 to the 6 grams of titanium. Okay, the very last step, it says, so we've solved part A, and in the last step, it says, tell me what is the percent yield. And we know that percent yield is equal to actual yield divided by theoretical yield, okay, multiplied by 100%. So we have our actual yield, which was 7.91 times 10 to the 6 grams of titanium divided by our theoretical yield, which is 8.94 times 10 to the 6 grams of titanium multiplied by 100%. And you can see that grams of titanium cancel out. Let me try this one. 7.91 times 10 to the 6 divided by 8.94 times 10 to the 6. I end up with, multiplied by 100, and I end up with 88.5% yield. So that's pretty darn good, okay? That's very good, as a matter of fact. All right, and that brings us to the end of Chapter 3. That does it. We solved all of the problems that were in Chapter 3, and there were a lot of them. So Chapter 3, mass relationships and chemical reactions. What did we look at? We started out by looking at atomic mass. Then we looked at molar mass. Then we looked at balancing equations, stoichiometry, so converting from moles of one substance to moles of another substance. We learned about the mole. And what else did we cover? We covered limiting reactants. We covered theoretical yield. We covered percent composition. And so all of these questions that you saw in chapter 3, these would all be considered fair game and very important content to test you on in chapter 3. All right, so that covers chapter 3. I'm going to stop recording.